Can you put on the WhatsApp group that you're about to start and then request people to join? Madhukar.
Hello.
Hi.
Yeah, hi, sir.
No, are you muted?
No, I'm not muted.
No, he's not muted, but I can't hear you.
Can you see me?
Okay. Yeah, I can hear you now.
Okay.
My speaker was in its lowest position. Yeah.
Okay. Sure.
So let's wait for 5 minutes because the
Yeah,
tradition is here. There'll be a
yeah,
few more
sure.
people. Sulagna is here and she's all ready to go. Okay.
Yeah, sure. So I'll be here and I'll wait.
Yes, thank you. Yeah.
Okay.
I gave the option. It's highly recommended.
There was miscommunication regarding the link. Yeah, I mean that also
One more physical audience a week. Oh, Gohan is there. Ah, you're not. Oh, you're not there yet. Huh? Will you also take the 6 p.m. No, but if you want to leave, you can leave at 6 because she wants. I want to stay to give her encouragement till the end. So it looks like we go on till 6:15.
Because I didn't bring cycle today.
No. But you can do one thing. You can stay at 6:15. I'm taking an auto back. Okay, I can drop you off.
Oh.
Where do you get off usually?
I live at Padu.
Huh?
I live at Padu. So if you can drop me at the gate.
Is it okay?
Yeah.
They drop you at the gate? Okay. So wait for a couple of more minutes and then you should start. Hey, Ramit. So whenever you're ready with the slides, give me the slides. Okay, whatever form it is, I will upload it. Okay, I will upload your video. Okay, because there's one thing that I'm planning to do, which I'm going to think. So in grading now, I've split that. Like the final exam grade will be whatever the quiz that I had, A little bit more, I'm giving more weightage to the thing. I will give you all the weightage and then everything, and your graded assignments, etc., will be every Monday, so that you could have an idea what the thing is. For grading the
There will be a quiz.
no, there won't be any quiz. That's in lieu of the quiz is what I'm making the write-up. Okay, so whatever the grade that I had, I will give it to whatever the weightage I had. I'm planning to transfer it to the write-up. So pay good attention to the write-up.
So what about extension?
For the,
I didn't attend it physically, so I don't know.
no, that I have. Okay, so December 7th is when I'm expecting. 7th, not 17th.
Oh, okay.
No. Only 1 week extra after your exam. You can't have any excuses for after the exam. But for grading the presentation, here's what I was thinking. And Madhukar, are you listening?
Yes, sir, I'm listening. Of course.
Okay. I see there is I'm going to get feedback from your mentor. That will carry a lot of weight in terms of 40% of the weight, okay, which will be based on your mentor's evaluation of your understanding, how have you worked, and so on. The remaining 60%, I'm going to split into 30%. I mean, 30% I'm thinking of giving. I mean, here is where I want your idea. For you guys to vote, I mean, to give your feedback. அதிலே கொடுங்க.
I can't hear anything if anybody is speaking anything.
Hello?
Yeah.
Can you hear me now?
Yeah, I can hear you.
Yeah, there's a little bit of echo. நான் இங்க மியூட் பண்ணிருக்கேன். ஓ இதையும் இது பண்ணட்டுமா? Hello, can you hear me now?
Yeah.
Yeah. So maybe 10 to 20%, as I said, participation. I'm going to give about 20% for getting feedback from the rest of you. I mean, you can vote. You can grade all the other people, other than yourself, the speakers.
Hello, sir. I am here online.
Yes?
This is Shubhavan. I am attending online. Is that fine?
Yeah, that is fine. That's fine. I gave you the option today, no? So so I was thinking, so maybe 20% I want of the only the presentation part, okay? For the mark towards the presentation part, I want each of you to grade the rest of the folks on how much you liked and learned from the presentation. Is that a good idea? You can gang up and vote all the same, or you can vote your conscience. So it's not a good idea. Okay. So what do you think, Madhukar, Shubhaman?
Yeah, I mean, if they have any suggestions, we can take them.
Let's be honest. I think this apparently this one was done by another course this time that has presentation as well. So when I heard from that faculty member, I thought, hey, why not? Okay, and so if not, well, there is Romit has reservations. It's not a good idea, I think. It's not a good idea.
I think something could be better.
It is good.
Right now, I can't think of anything. But
Okay. Okay. So I will, not do it. Okay. So good. So everything will be then 50% is based on the mentor's feedback. The other 50% is I've listened to all the talks. Okay. Maybe 40% I will evaluate how I felt about it. Okay, and then maybe 10-15% based on how your participation, attendance, and how much you have interacted in terms of questions and so on. So those things I have made a note of. Okay, so that's how it will be. Okay, yeah, you can start.
can I start?
I want to make sure that I have started recording. Yeah, go ahead. Yeah.
Yeah. Hi, everyone. I'm Sulagna. Today I'm presenting this paper, Minimal Modification of Deep Neural Networks Using Verification. I'll straight away first go to the overviews. I will first go to the introduction, then will provide some background, then overview of a simple DNN deep neural network, what is DNN verification, then what is modification of a DNN distance, then I will come to the crux DNN minimal modification problem, and then I will show, or I will present this part, how we convert the modification problem to a verification problem. Watermark resilience and minimal repair, these are two use cases of what I'm going to present. Evaluation, the implementations of the previous and related works, conclusions. Introduction. Needless to say, deep neural networks are quickly becoming the state of art in many domains of computer science. We have seen in industry, we have seen in academia, in computer vision, speech recognition, game playing, everywhere. So this is causing a growing need for modification of already trained DNN. So we have already a DNN in our system. We are having some procedure being done with it, and suddenly suppose there are some urges, there are some demands arising of modifying that particular DNN. What could be the impetus of modifying a particular DNN? There might be a case where we will find, okay, this DNN has some error in it and we have to modify that erroneous part. Or there might be a case that DNN is uh, failing to satisfy the motive for which it was built, so we need to modify. So these are the two paradigms. One is machine learning as a service, we call MLAS, where vendors, this is how working ecosystem in industry with DNN goes. Uh, in specific, vendors release the fully trained DNN, and clients then fine tune the DNNs according to their own needs. Patching. Patching is a DNN has already been produced. It is in operation. The user detected some bugs and he wants to modify the DNN without significantly changing the other behavior or other implications of the DNN which is currently present there. So what can be a possible solution? If we retrain it from afresh, it can, the final DNN which we are getting after retraining may be very different from the original. And for existing approaches which are there to modify, they are mostly heuristic based and are not guaranteed to produce the desired results. So here comes the paper which is suggesting we propose a novel approach for tackling this challenge based on neural network verification. Backgrounds. So here we are converting the DNN modification problem to a DNN verification problem.
Yeah, one question I have.
Yes, sir.
So normally, go back to the previous slide. Okay, and I don't know what you mean by modifications, which will probably you will
Yeah.
explain later on.
Yeah.
But is this even a, I can see the need for it, but I mean, I can wait till you define what it means and how you modify, because DNNs are notoriously already, people don't understand why it behaves in a, when it classifies certain things, no one has a clue as to why how it behaves.
Yeah.
I mean, why it produced that thing. So being you don't know why it works in the way it works, is this a good idea? I mean, if you try to change something that you don't know how it works, because they are black boxes, you might end up damaging it a lot more than if you did from scratch. And maybe that will be answered when you define how it is modified, or you have some answer
that
to
is
it.
why we will go to the minimal modification part.
Okay.
So I'm continuing
Okay.
with this.
Yeah.
Yeah, so we are converting the modification problem to a verification problem. Just as a first layout, I'm just analogically defining it in 2-3 points. We construct a new DNN from that existing DNN. I will explain how we do that. Then we will pose a verification query on that newly constructed DNN. Then we will see if the verification query is sat. The verification query is sat if and only if the original DNN can be modified in the desired way. So we are not actually we are posing this modification problem as a verification sat problem of that newly constructed DNN. So we will go to that. Use cases, again, like specific use cases to mention. One is authentication of ownership. We will come to its implementation at the end. That is DNN watermarking. Watermarks are secret inputs to a particular DNN. If you give that input to the DNN will react in an unexpected way. So this watermarks are flagship to a particular DNN, and we want to check the resilience of the watermarks or creation of the watermarks or removal of the watermarks given this approach, this modification to verification approach. There comes a question: does conscious modification to DNN accidentally or intentionally remove the watermark? Like suppose you need to modify the DNN because it is inherently erroneous and we found that error and we want to debug it. If we do that for the sake of the DNN's performance itself, does the DNN lost it? Does the DNN lose its identity? Like, can we say that, okay, now this DNN is something different? Like the watermark is the identity code of the DNN. So if it is losing the behavior, if it is losing the thing that, okay, to this watermark, it is not behaving in the proper way as it was doing previously, we can say that the DNN has lost its identity. And we don't want this to happen by any conscious modification of the DNN.
Wait, so I have a question.
Yes, sir.
Go ahead, Shubman.
Yeah, so like for example, if like suppose we were classifying the Amnes data set, okay, and suppose it was erroneous, but now after our modification, it's not erroneous anymore in classifying the digits, but now it cannot work the way it's supposed to on the watermark, like you were saying. Then is it not a desired outcome?
Is it? What?
Is it? Can you repeat the last part? That didn't come out clearly.
So that's not a desired outcome, is it?
Or is it not a desired outcome?
Even if it is modified, And suppose there were some faulty behaviors, the faulty behaviors are checked by the modification. But after that also we are seeing that the DNN, the modified DNN is not responding properly the way it should respond to the previous watermarks. We can still not say the new DNN is watermark resilient to the previous one. That is what I am trying to address. So the watermark, the DNN watermark identity behavior should be preserved while we are doing the modification. Right.
So like that's an additional constraint on top of it being able to classify the amnest data set in my example.
If I understand Shubman's thing, let me try to paraphrase, and maybe if I'm wrong, you can jump in. No. I also got a little bit confused in the same way. So first you said the DNN modification problem. This is a special instance of that, okay?
No,
this is, so what he's asking, which is the question that I had too, I understood the first three, 1, 2, 3, okay? So there is a desired way in which you want to modify it, okay? So the first one says you define the problem so that if it is set, if and only if the original DNN is modified in the desired way.
Yes.
I mean, I'm assuming the desired way is going to be specified somehow. Now, when you say the use cases, the first one that your authentication ownership, is that the that you should preserve after modification the ownership authentication? Is that your definition of the desired outcome of your modification, or is it something that no matter, that your any modification should always, in addition to obeying the that it does the modification desired way, that this should also be preserved?
Yes, I mean, I pose this after this, but it does not mean that this desired way modification should be performed and then only this is coming. This you can, like, this is the, like, DNN authentication is the inherent need of introducing the DNN. Suppose somebody is working in
that I understood. So is this an additional requirement for your modification? So I think that was what Shubman's question was.
For modification, I need the verification queries to be satisfied, and that's it. So that is
okay, that is not clear. So is this, oh, he is here in person. So was that your question as well? This is an additional requirement. Yeah, I don't think your answer was very clear. So the basic thing is, is this an instance of the way you modify, or is it an additional requirement?
This was a requirement for, this was a requirement of the DNN, like watermark removal, what we are saying. So I think I could be a bit more, like I could go a bit deep. That is, we are checking the watermark resilience. I mean, suppose if we are removing a watermark, like how long will it take for us to remove the watermark by modifying the DNN? And we will say
that's an instance of your modification.
Yeah.
Okay. I think it's an instance of the modification. Is that correct, Madhukar? Madhukar?
Yeah, yes, sir.
No. Is that understanding that this is just what authentication of ownership is one use case of a modification?
Correct. It's just one use case of it.
Okay. Got it.
Yeah. So I also had a question, Sulagna. So you talk about modification and then you immediately say that we talk about verification. Why not solve the modification problem itself? Would you want to talk about that? Or?
Suppose, okay, diagram will come later as I suppose,
so if you're going to talk about that, then it's fine, right?
Yes, I'm going to.
Yeah, somewhere that should come out,
Yeah,
right? I mean, you took a problem and you're immediately modifying into another problem. So
yeah, I mean, this modification is leading us to some other problem for which we need some other way, and this paper is approaching towards the verification. So
okay, sure. Okay. Yeah, carry on.
Yeah. So this question, the answer could be like this resilient watermarks. I will come to that also. And also suppose we are modifying the DNN, the minimality of the changes, the minimality we can assure in that way. Suppose we have a DNN for which there are some faulty points. We will find a modification, then verify the network, and suppose So for some of the faulty points, the DNN is right now behaving properly, but there are some additional faulty points. We will add them up to the previous set of faulty points and we will repeat the exact same steps. If that converges, we can say that minimal modification exists. And for implementation of the whole thing, we have this Python framework, Marabou verification engine, and LP solver, Gurobi LP solver. We will come to that, why we need LP solving. So this is just this is just a highlight of what we have already done. This notations we have used in this while explaining the later part. Layers are n, SIs are dimensions of each layer, VIJs are jth node of layer I. This is entirely a VI, and WI is all the widths which has been assigned to the nodes of VI of the dimension SI, SI minus 1. WIJK is a particular element of that weight matrix for that for that particular layer, and bias vector here for our assumption it is 0. So hidden layer can be represented as, we are taking ReLU as an activation function, although this paper claims that their process is, I mean, the implementation they have suggested that is the activation function agnostic. So here we are taking ReLU as a standard activation, and this is for each of the hidden layers, and the final output layer is having no activation in it. DNNs are usually classifying this way. We are having this set of all possible labels, and suppose some input is given as VI, this is classified to the label LI if this the value of LI is maximum among all the possible nodes of the output layer. Yeah, so this is a just simple illustration of simple DNN with one hidden layer, one output, and one input layer. This is the input, and given that, the second layer is computed with the ReLU as this, and the output layer is computed as this. So the output layer is having, I'm not going into much of explanation of this. This is already done. -2 and 2, and since this value is bigger than -2, we are classifying the 0.34 to level 2. Neural network verification. So this is also a brief background about verification. Let P and Q be predicates as constraints over neural networks input and output respectively. P has a set of inputs of interest. So here are inputs are given, and Q encodes the negation of a desired property. So our question will be, does there exist an X such that Px and Qnx both holds? Now Q encodes the negation of a desired property. So if we can prove that this is unsat, that means there will exist no such point for which this properties hold. And if we can't show that, we can show that there is existing a violating point, suppose x naught or x prime, for which like the negation happens. That is the thing. And yeah, DNN verification is NP complete. Next comes to modifying DNN, what we were talking about from the very first slide. The state-of-art verification approaches till date, they have done what they have done is, they have taken, like, this neural network is fixed, a particular input x naught is sought that satisfied certain constraints. So we are trying to get an input given the neural network, and we have the query assigned in our hand, and we are trying to get such an instance, or we are trying to get that no input exists such that this query is satisfied. The approach the paper uses is, our DNN is given, the input or inputs are given, we search for a different DNN such that certain constraints hold. Now, what is it doing to the previous DNN. Since we are posing the query on it, since we are trying to see whether this DNN is solving the satisfying the query or not, how is it related to the previous DNN of our interest? Now we will try to, the modification comes in this way, we will try to modify the previous DNN to such a DNN which holds these constraints, and this modification should be such that this new DNN is close enough to the DNN of our interest. So we will take this approach to verify this and to get a conclusion about the previous DNN. Yeah.
Yes, so the constraints for the new DNN should hold on these inputs only, right? Which are already given for the previous.
These inputs are for the older DNN, I mean the DNN of interest. We
Yeah.
are constructing, we are searching for a different DNN. This is not entirely a randomly different DNN. This has some relation of derivation from the older DNN. So we will search for this DNN, and we will have this input points, and we will have this certain constraints.
Yeah.
Now,
okay.
how this new DNN we are forming, we will show.
So in the new DNN, we will feed these same inputs and the.
Not really. It will carry forward the legacy of the older DNN. The older DNN will have this inputs, and it will. I mean, I will show the illustration maybe after that.
Yeah, yeah. Okay.
But its input are not the 6 knots, but it will carry forward.
I think the bullets, the way that you use constraints is a bit confusing, okay? So are the constraints, okay, first you say is sought that satisfies certain constraints, and then you say such that certain constraints hold.
Yeah.
Are these two constraints the same?
Yeah, same.
They are the same.
Yeah.
Which means, because you started out by saying the motivation and the need for modification is, at least one of the motivations, was that the DNN was not working in the way that you wanted it to on certain inputs. So you want to change the original DNN in such a way that it presumably will map those inputs to the way that you want it. Then that cannot be the same constraints, no? So your the second constraints will fix the violation of the thing, no?
This will fix the violation for previous DNN.
So that's what, you say X naught is sought that it satisfies certain constraints.
Yes, first we had this X naught as, like, we are finding the X naught, and in this, for this, we have the X naught given. For the given DNN, we have the X naught given. We are searching for a different DNN, and we are trying to satisfy the queries.
Yeah, presumably for those X naught, the original network was not giving the right answers. Yeah?
Yeah.
Huh? You got it, yeah? Okay.
Okay. Yeah, so this is the DNN modification problem. We have been given a set of fixed input points. Yeah. And this is N is my previous DNN. And Q be the predicate over the classifications of the points. We are finding a new DNN such that this predicate holds, and such that the distance between N and N prime is at most some delta. I mean, it will not deviate much from N to prove what N could not. It will stay near N. The N prime will stay near N. Mathematically, it will stay near N. And it will try to verify this predicate Q N prime excis.
Wait a minute. So here, N and, okay, the distance is between, is this a distance between the two networks or the output of the networks?
Two neural networks.
So you want the modification to be also somehow not too far apart. Okay.
So we will
Okay.
define
But
the
but
distance.
nonetheless, whatever modification that you make has to satisfy those
Yes.
other constraints. Okay, that I got.
My question is same. Like you define the notion of distance between two.
Yeah, I will define the
Yeah,
notion of
okay.
distance. Yeah.
Was there any other questions?
Okay, so for like we are trying not to deviate much from n and n prime. So very naturally, we will first try to seek for such a modified n prime, which will share the same topology with n. And this modification problem is trivial if the Q, this original network holds this Q. In that case, n and n prime are same. DNN distance, as we used it before, but we haven't defined yet, it's just N1 and N2 are my two DNNs. Same number of layers, same number of neurons, as we have assumed already for these two neurons, for these two DNNs to have the same topology. Now we define the L distance between these two as this. It just boils down to the fact that we are computing the distance by taking age-wise difference. It's like suppose for ith edge, 1 to I minus 1 are is it visible? S1 I minus 1, 1 to S1 I. So what we are doing is, okay, this is, what is this? This is for the first neuron, for the ith, for the first DNN, for the ith layer, this is the weight which is coming from the I minus 1th kth node to ith layer's jth node. And this is the same for the second DNN. So what we are doing is, we are taking the difference in a L norm space, and we are summing up all the differences together to the power 1 by L to get the distance, to formally get the distance of L distance between N1 and N2.
So which means, go ahead, yeah.
So we are never changing, we are not removing or adding any nodes ever,
No,
right?
we are trying to
Only-
fix the same topology.
I see.
Fairly
Because see-
restricted. So the only thing we are allowed to change is, from what I understand, the weights.
Yeah,
and
just
even that is constrained by this
Yeah.
distance.
Yeah, so we're not changing the biases either.
No.
Okay.
So actually, we are trying to attain, if possible, we are trying to attain the modification being within the nearest periphery of the already given neural network. Because if we deviate too much from it, there is no question to return from that. Then what is the point of the far-away neural network satisfying the constraints? I mean, that is in no way, that will in no way be close to what has already given. So yeah, suppose these two are your neural networks, just as an instance of this definition. The one norm is simply you're taking the corresponding age weight differences, their modulus absolute values, and summing them up. And the infinity norm is you're taking the max of each of the difference components. So these are two norms. Specifically, we will use the infinity norm, because I will say later we will go to, we will have to, or we will kind of change this problem direction to a optimization problem, where we have to solve an optimization, and for that to have this finally will give us a set of linear constraints, where this will have a set of constraints which includes this modulus. So solving an optimization with without this modulus absolutes are actually easier than solving this absolute
Yeah.
values.
What is capital L here? So
It's
L is a parameter,
L
it
is
seems.
L is like that L norm space we are taking, like the
Yeah, you could.
yeah,
Which
it's the
particular metric
yeah,
you are
yeah,
using, right?
Yeah.
Yeah.
The distance metric I'm using is a L distance I'm
Yeah.
denoting as it.
So in this example, can you demonstrate the sum that WI1JK using the edges like?
Okay, sure.
Yeah.
Yeah. So suppose the I here is what? This is first layer, this is second layer, this is third layer. Suppose for second layer, W2, I'm doing this for one layer, say, W2, J and K. What is this J and K? J is the entry of this, J is the node of this layer, and K is the node of the previous layer. So I'm taking what? Uh, I don't know whether it is feasible or not. V211. Just remove it right now. I'm not taking this one into account. V21 to V11. I mean, from V11 to V21, the age which is coming, I am naming it as W1, sorry, W2 to 1, right? So W, the layer towards which the age is going, the node, the end node, and the previous node of the previous layer. So this is the setup of Wij, and the same way this is the thing. Like for the second DNN, for this is the particularly this is the edge which is coming from the kth node of ith layer to the kth node of I minus 1th layer to the jth node of the ith layer. Previous layer K to present layer J. This is the edge. So suppose this to this, this and this I'm subtracting, I'm getting this component wise values. Okay, if you are asking me to expand this, this is basically I am going from first to I minus 1. I mean, suppose you are taking the ends into account. Okay, ends of all possible ages into account. So this you are having, and for each of the possible end layers, you are computing all the like this the second one, the second component. So for first layer, you will obviously get no edge. From second layer, and from second layer, it will start gathering. So that is why this is gathering the layers. This is gathering the starting point of each node, ending point of each node. This is gathering the starting point of each of the nodes. Fine? Yeah.
So suppose in the second network,
Yeah.
you multiply the weights by 10.
Yeah.
And in the first, from the first layer to the second layer, and in this from the second layer to the third layer, you divide the edges weights by 10.
Yeah.
Then the output will be the same of both the neurons, both
Yeah.
the neural networks.
I mean, suppose.
So that is 1 there. So the first stage is 1. So in the second is make it 10.
Sorry, which one you were saying?
So from from the first stage, that is 1 there in the first neural network. So make it 10.
Yeah.
And similarly, that is minus 20.
Yes.
That,
all this, sir. Yeah.
And similarly, that is 1 by 10.
Yeah.
Minus 1 by 10.
Yeah.
So these are only getting multiplied. So the ending result will be same. Because first you're multiplying by 10 and then you're dividing by 10.
Yeah.
So, but here the...
Yeah, no, biases are not changing.
Let's say biases 0.
Biases are not changing.
Yes, so it would not be the same.
So here's, you are saying that it is getting changed, but...
No, the output is not changing. So the neural network is not behaving differently. But your distance, what will be the distance between the two neural networks?
Distance, if the ages are getting changed, and if it is this value is coming up to be something non-zero, we will treat both of them to be different neural networks.
Although their result is same.
Yeah. Oh. Because the topology is different, right?
No. In this case, the topology was not different.
No.
Only
the weights are
different.
different.
If I understand correctly, then the distance will be 0 in that case, no?
No,
Huh?
distance will not be 0.
Yeah, maybe it'll help
Yeah,
if you, Sulagna,
Yeah.
it'll help how you computed for the one case. Okay, please go step by step to see how you computed for the
sure.
N1 minus N2, and then we'll come to Arpan's question.
Yeah.
So I'm still stuck at this one. So explain the first equation in
Okay.
that.
So N1 minus N2 norm 1 is, suppose, this network, and this is a completely...
That we understand. So go, why, how did you get minus 0.5?
This
No,
is the
here
first...
in the
Yeah,
equation, that's what you explained.
Yeah.
How did you get minus 0.5? How did you get 1, minus 0.5,
True, yeah.
0.5, and so on? Yeah.
Suppose for this, I'm taking the first stage of the first bridging
Correct.
layer,
Yeah.
first bridging this 1, and correspondingly this is 1.5. So you're just subtracting this 1 minus 1.5.
Okay.
You're getting minus
so
0.5.
that's corresponding edges you're
Yes. That is
identifying,
what-
and then the weight you're subtracting. That is good enough.
That is
Yeah.
what we have defined here. And
Yeah, but you should have, then there is a sum, no? So where did you get the sum? Because, that's what you're summing there. Because you're only doing one. You're summing it, or all the differences in the first
Yes.
layer. That's fine. Yeah, okay. So if it is, yeah, that is fair enough. So N1 minus N2 for infinity means, why are you taking max? Because there is no max there in your
maximum of all the
equation.
deviations. No, it is just a metric we are introducing, and the intuition behind is we are taking maximum of all possible deviations happening to the given DNA.
So this is how L infinity norm is defined.
Yeah, just a minute, Madhukar. What did you say?
So this is how L infinity norm is defined. L1 is the pairwise difference, like how you can see. L infinity is defined to be the maximum deviation.
Described it this way. Okay.
Yeah, L infinity is defined to be the maximum deviation.
Okay. Now, another question that I had was, L, for example, in this case, including the input and the output layer, there are 3 layers. Okay.
Yeah.
So if I had, because the definition of that distance has only 3 summation, okay, over I, J, and K. I being from 2 to N1. I don't know what N1 is, okay, and I really don't know what Sij, Sj, Ij minus 1 are. What is S?
So N is the number of layer. So N1 is number of
N
layers.
is the number of layers,
Yeah, of
okay.
First DNA.
Yeah, and S1.
S1 is the dimension of ith layer.
Oh, it's the number of nodes in the ith layer.
Yes.
Okay.
So
And Sj is the number of nodes in the jth layer.
yes.
Oh, okay. I got it. Yeah. So that's why they are summing it over all layers then. Yeah.
Yeah. And that's why we can introduce this metric.
So as you increase N, as you increase L, you will be considering more and more the summation of difference between more and more layers.
Yeah.
Is that right?
Yeah.
Yeah, okay. Yeah. The effect of increasing L, that L distance, the norm, will you be, yeah, but here there was only one series of summation, correct? So I was wondering if L has something to do with the number of...
You're asking about L or N?
L.
Oh,
L
okay.
for love.
Okay.
Yeah. So does that have nothing to do with, you're
Yeah,
always summing
because
all of them, correct?
it's just the way we calculate. Suppose for L2 norm, the way we calculate the Euclidean distance, the same norm.
No.
we are
Suppose
using
I
for-
did L2, N1 minus Ln instead of 1 in the equation.
Number of,
suppose you had 2 there.
Yeah.
What would be the difference? Tell me.
It will be like this minus the square, like individual differences square, and then the square root. Yeah. I mean, yeah, I mean, it should be to the power L, whole to the power 1 by L. Yeah. Oh, okay, I mean, I just followed the convention which they have. So it will be like component wise, it will take the difference, then it will take the Lth power, then after summing up all the Lth powers, it will do the 1 by L. Will take the Lth root. So that is how L norms are calculated for any L, for any finite I.
Okay.
So yeah. Shall I go to the next
Any questions?
questions? So the as we already have this modification problem, and we have defined the distance in our case, the minimal modification problem is for this same way we initialize that the DNN is n, and x is a set of fixed inputs, q denote the predicates. The minimal modification problem is to find a new DNN that solves the DNN modification problem such that for every other n double prime, it holds like the n double prime, which is also solving the modification problem. It will always be farther than that n prime from n, given that L norm. So that is the minimal modification problem.
Okay.
Yeah, I mean, we can get it by binary searching, search finding procedure. Suppose we have got some n prime, which is solving the modification problem for n. We will start taking the half length and trying to see whether it solves the half length one solves, or if not, so we can proceed in such way. Minimal modification as DNN verification.
So the binary search will be on the value of L.
Yes, values of n primes.
Oh,
N prime,
that is, yeah.
n prime 1, n prime 2. Maybe you can, if you say if it converges at that. Like suppose n prime is the one which is solving the modification problem.
Correct.
We want to see whether this n prime is a minimal or not.
Yes.
For that, I am coming halfway and seeing whether there is any such.
Yeah, the minimality is on the distance, nah?
Yes.
The distance metric.
Distance of this, yeah.
Yes.
N prime and n.
Yeah. So you will
Okay,
you will
given
start
the
with
L.
some max, and then you will.
Yes. I mean, starting with some random.
Random. See, binary search usually requires that you, when you're binary searching, something has to be totally ordered. Okay. What is the ordering that is being used here?
First, I got some modification.
Yes.
And according to the modification, I got some n prime.
You got some modification for some distance. What is that distance? You choose randomly some distance? Some L?
Actually, so I mean, we are randomly choosing some extra additions to the edges and then trying to optimize it.
L is fixed. Yes.
Yeah. The modification you are asking whether it is random or not.
No. My question is about binary search. What does a binary search of an array mean? It means that there is a total ordering. Okay.
Yes.
So I mean, so you will, when you're searching an array for an element using binary search, you will first pick the midpoint of the array.
Yeah.
Right? So you're using the index, which is ranging from 1 to a max of n. Yeah. You see if it is, you have the element in the middle.
Yeah.
If that is not, it is greater, then you look at the higher, the upper part of it, or the lower part.
Yeah.
So what is the parameter on which you're doing binary search here? That was my question.
Of the distance of the neural networks, which I'm getting, suppose.
That requires some minimum and max, nah, if you're doing, yeah?
Because I'm keeping the L norm fixed. So,
L is fixed, okay.
Yeah. So I'm posing some modification and getting n prime. And given in that L space, I can define the distance from n to n prime.
So you will, okay.
Then the way how I saw it is given n, I got a modification. I have my L space. Now in this L space, I got the like modified DNN, and I'm trying to suppose this is some certain value. I'm trying to coming halfway and trying to find
Halfway of what? Halfway of what?
this distance of the neural
Yeah,
network.
so you will, but at the first time you do, you do some randomly, you modify it. Huh?
Yeah.
And whatever distance that you get, then you take the divided by 2, and then you see if there is one.
If there is any, yeah, if there is one other n double prime which is satisfying this.
If not, then you will increase the distance.
Yes.
You will increase that
Yes.
distance and so on.
So it's like the distances of the neural networks given in this L space. So, yeah. Anything else here?
Okay.
Yeah. So I'm posing the modification as a verification problem. We are trying to minimize this difference, L difference of modified and the new one, while this given predicate constraints is still satisfied by the modified neural network. So now I am coming to how this modification we are doing. So in that sense, suppose we are modifying all the weights, given the biases are 0, I am modifying the weights, adding some WIs to each of the weights for the 8 of the ages in this TNN. Yeah. So we are trying to find a minimal assignment for WI so that this modified neural network satisfied these predicates. Suppose this is my given input and this is my predicate. What it is saying, like for the given input, it is saying the label should be 1. Because remember, when I had my previous neural network, the simpler one, where was it? Yeah. So it classified to the second level, classified 3-4 to the second level. So as we are trying to, as we are trying to take the negation of the constraint and then trying to get the answer. So we are trying to classify this point to the first level. So what I'm doing is, this is my modified neural network. So the V3 one will be calculated as, this is 1 plus W5, 1 plus W5 of this thing, and minus 1 plus W7 into this thing. Now what is this? This is 1 plus WI into V11, 1 plus W1 into V11, which is 3, and minus 2 plus W3 into V12, which is 4. So this is V31, first part, and second part is coming similarly like this. We are taking the ReLU for the hidden layer. So this is the computation for V31, the first final layer, first node, and this is the computation for the second. Now see, we are getting after modification.
Yeah, but why is the goal here finding minimal assignment? What do you mean by minimal assignment for WI? The smallest weights, you mean? For each of the weight? What is minimal assignment for WI?
Actually, not for each of the weights I'm counting whether the entire, suppose, okay, I'm taking this and other neural network. I mean, this is the modified, that one, the original. After weight change and all and have been done, I'm taking the L norm to be minimal. Not each of the, it will it will blow up.
Yeah, the minimal assignment means that one that makes the L norm the
L norm of
smallest.
the two neural networks to be minimum. So this is the computation of my final layer. And as we can see, we have introduced so much of variables. It has gone. ReLU is a nonlinear activation function, so it is highly complex and high dimension. So to solve a problem, we are inviting some other problem to it. So what is the possible solution for that? So we can propose.
Because that one is not even, you can't even just send it off to LP
Yes.
with the model thing because of the nonlinear
Yes, it
ReLU
is.
function and so on. Yeah.
Also non-linear, also high dimensional, so we can't do anything. So
Like 8 weights, so
yeah, and this is the simplest of some of the simplest NN format we can see. Things can go more complex. So we can limit the changes of bits to a single layer. So we are trying to, formally we are trying to simplify, and from the simplification we are trying to get the modification which satisfies the verification problem. Suppose Wi be the layer, be the only candidate, suppose Wi be the only candidate weight matrix of N to modify. I have different weight matrices. Suppose for N many layers, I have N minus 1. So I'm choosing one particular weight matrix, and given the fixed input, from 1 till V minus 1, it will remain the same. Will remain the same. So we are just changing the weights from, just to show it, we are changing the weights after this I minus 1th layer. That means the ith layer. So for the modified network, all the layers from 1 to I minus 1 are same to the original one. Just at the layer I, this is the like computation of the ith layer nodes. Vi prime is ReLU of Wi prime, Vi minus 1 prime. So how is it getting calculated? I'm taking some extra variable weights which I will try to optimize, and this is the after applying ReLU to it, I will get the Vi prime, which is potentially different from Vi of the original node.
clarify, the weights are coming in towards the ith layer or going out from the ith
From
layer?
I minus 1 to I.
Oh, okay.
Yeah, so this way you go from left to right.
Yes.
Yeah? So you
Yes.
first see first
Till I
layer
minus
change.
1,
I mean,
everything is.
yeah, input of course you can't
Yeah.
change. I mean, from the
Yeah.
second layer onwards, and whenever you're changing at a particular ith layer, you assume that you've
Yes.
all the rest remain
Yes.
the same as what you had
Yes.
done before.
Just
Yeah.
ith layer, I'm making the change to happen. So for this fixed given input, we construct from this part, we construct a new DNN. Remember, we had this N prime, which was showing this. From this N prime, we are constructing another new DNN, which is taking this as my inputs, like the weights as my inputs. And we are constructing it into such a way that followed by the inputs, the second layer computes this ReLU, and then the I plus 1 to N, all the layers will remain the same. I will show how it is happening. This was my modified N prime, and this is my N bar. Suppose for the modified N prime, after the first modification, suppose what was my V31? What was my this? This was 1 into this into minus 1 into this, right? So 1 into this minus 1 into this. And this is what? V21. This is what? 1 plus W1 into 3 minus 2 plus W what? Minus 2 plus W3 into 4. So this is how it was calculated. Now, if you just do some manipulation to it, 3W1 plus 4W3 minus 5 minus ReLU of 3W2 plus 4W4 plus 2. So now, see, look at it. Look at this part. And try to construct a new neural network with this ages as inputs. What can I do? I can take W1 to W4 as its input. Now what I'm doing is, see, I am assigning the age weights as per the coefficients which has come. And then the extra term which is there, I am assigning it as a bias. So what, see, essentially it is computing the same what this was computing. So essentially I am transferring the modification, from the modification, I am trying to get another n prime new neural network, which takes input. Somebody was asking me whether the new neural network is taking the same input. It is taking the same, it is taking the modification of the edges, but it is carry forwarding the legacy of the original network. That is what I meant back then. Right? So it is like, it is carry forwarding the legacy of the modification which has been showed here. So this is the changed, modified slice of the thing which right now we want to focus on. Now,
first layer?
Here?
In the first layer of the left one.
Left one.
Yeah.
This is 3 and 4. We had the original network.
Yeah, okay.
3 and 4 was its original input. And this is the weight modification to it in one single layer.
So those those inputs now became the edge weights.
Yeah, this age weights became its inputs.
Yeah, yeah.
And I'm making it in such a way that after that, whatever is happening to whatever layer, it will remain the same to whatever has happened to the previous one.
Yes, yes.
So that's how you're computing the weights for the new
Yes.
network.
Yes.
Now, okay, this is good. So you're going incrementally.
Yes.
Okay, that I understand. So it is less complicated. But there's no guarantee that this is the minimal modification as per the L distance. Is
right
there?
now, we have no information about this WIs.
Yeah.
So the modification, whether it is going to be minimal or not, that entirely depends on this WIs, right? So suppose, what is the difference of weights, like given the original network and given this network? See, what is the modification? What is the L infinity norm of?
Yeah, no, if you're going to talk about that later, fine. So right now there is no.
Yeah.
So how the minimality comes,
Yeah.
you will address later on.
Yeah, I will just now address.
Okay.
Yes, some of those variables or max of the absolute values of WIs. Yeah, so see, now I am having this constraints in my head. Max of mod of WIs should be equals to some delta, right? So, see,
That's what you're getting at. Yeah.
this is my verification query. This is what is coming. So, and my Q was like to classify it to the first level instead of the second level, right? So the resulting DNN verification problem is sat if and only if the original DNN modification problem is set. Okay, so this I have shown for a single point, what is going to happen, how we are structuring the network. Still one point I am yet to address, I will do. What if in your set of inputs, you are having more than 1 points? How to address that case? So for that, what we are doing is, we are...
You mean more than one output?
Inputs.
Outputs, yeah? Here already there are 2 outputs, no?
No. It is like, see.
You did it for a single input.
Yeah.
If for multiple inputs,
yes.
You're saying.
Yes.
Oh, okay.
So
for multiple inputs. Okay. Yes, yeah.
Yes, this is
Multiple input vectors, correct.
Capital X is within second bracket this thing. So this is one point. So we will just take carbon copies of this networks and we will assign weight to one of the particular layers and go in a similar way. When X contains multiple points, we simply duplicate the DNN that we construct n times, creating a copy for each of the X and treat the result as one big DNN that is passed to the underlying verification network engine. So just to make it fully connected, you can introduce some new layers across the like suppose this is the one input point, second input point, the nodes are corresponding to that. Across nodes, you can just assign the weights to be 0. So you can construct a big DNN in that way. Yes.
Yeah. Okay.
Yes.
But only the input.
Yeah, I mean,
Multiple
now
input changes,
I
yeah.
just was yet to address one more point. We are saying that, okay, we will focus on just changing one particular weight matrix. Now, which particular weight matrix should we choose to make our life easier? So again, for that, another simplification is, okay. The deeper the layer that is being changed, the fewer neurons there are in the resulting DNN verification problem. Because see, if I'm changing, if it had some 3-4 layers, if I'm changing here, then I have to make the computations which will carry this WIs again and again for all the layers. So if changing one layer can solve my problem, can boil it down to some simplified version, why not changing the later one? So that way, yeah, I am saying, suppose you right now, I'm convinced that changing one layer will potentially be able to solve the modification problem. But right now, I still don't know which layer to change to make the scenario easier. Now, if I'm changing, suppose the very first weight matrix, suppose this one I'm changing, and this has some other layers, 2, 3, 4. Yeah, so next you are constructing this n bar, another modified neural network with this WIs as its inputs, and it will be bigger enough. And it will carry this WIs from the beginning. So till the output, you will get a very large equation because each of the input, each of the hidden layer nodes will have value to it. So it will be like very big a computation, right? So yeah, the deeper the layer that is being changed, the fewer neurons there are in resulting DNN verification problem. So this is easier to solve if the changes are limited to the output layer. Like we are just concerned about changing the layer, which is between n minus like layer n minus 1 to layer n. That weight matrix I'm focusing on. Yeah.
Yeah, but
Because you have this computed till. I mean, you have these values in your hand, right? Till now, you are done already because you have the input fixed. You're just changing. You are adding variables to the like extreme end. So what will happen is the n prime which you are constructing will have some certain k many inputs, and it will have some it will have some k many inputs, and it will have some one hidden layer to get this computation. Not layer, but
weights.
Not nodes, the ages.
No, only the weights.
Age weights.
Only the weights are changed. What do you mean the nodes are not changed? In the new DNN, there are new nodes, correct? Huh?
These are the inputs of the new DNN. Right? then you have to construct it in such a way that, see, like you're having this W1 to W4 there, and you are with that you have in hand that you have to have your output to be what the value of V31 and V32s are. So,
in the previous example, when you changed the
this
weights,
side.
yeah, those weights. Yeah. Oh, sorry. So the new DNN had the WIs in the input layer, right, in the first layer.
Yes.
So, but if you if you get the N bar for this DNN, where would the WI layer be?
But this is not the final layer of my N bar, right? My N bar, see?
No. Yeah.
See, this and suppose this and this are not the same, right? This is modified in such a way that you will get what you were getting there.
Yeah, yeah.
Right.
That's right. Yeah.
So, I mean, after that, the value will remain the same.
Yes.
But it doesn't necessarily see this is the input, but this age weights are 3, 4, 3, and 4. So different.
No, that's okay.
And then you are introducing bias.
Yeah, no,
And
that's okay, but that's not my problem. My question. My question is that, like, where would these WIs be? In which layer of the new DNN N bar would these WIs be placed? If should we change this second layer weights or the weights after the second layer?
Exactly, it will give you the output constraints. Yeah.
Oh, you'll add in between. Oh yeah, we'll add. Okay, yeah, okay.
So you have these two values you will know. Suppose till the like the air till the n minus 1th layer, you know the values. So just after that, you will just construct one way.
Okay, okay,
right?
yeah, I understood. Yeah.
So what happens is, suppose if
But one question is, I know that here you said that typically, so there the previous modification was
Yeah.
going from left to right.
Yeah.
Correct.
Yeah.
So you do that all the way?
Yeah.
I don't know what the final algorithm is, but you know, suppose
Yeah.
you do it all the way. Now, but then here you introduced, okay, that you know, the deeper the layer that is being changed, the fewer neurons that are in the resulting. Fine, that I
Yes.
understand. So now I mean, this picture is implying that you're doing it from right to left. Is that the
Computation
case?
is from left to right. Just delete this from your mind, and you just think that you have the value of this and this to you. Right. So what happens is, I have till this, I have this weights. So the input weights I'm getting, I will make sure the further neurons will have the same value after, suppose W1, W2, W3, W4.
My question is simple. Do you do this procedure from right to left?
Yeah.
Okay, if this does not work for optimization. Okay, so the paper did not go till that. There is a related work scope where they have said we can explore the different layers. We can explore the different layers or multiple layers together to see what happens.
Sorry, what was the question? I missed that question.
Well, the question is, you know, so this one is suggesting that you go from the output layer, okay, this modification that was described in the earlier slide seemed to indicate the modification is done from left to right, layer by layer.
I think in their experiments, they just modify one layer.
They modify only one layer. Then how do they pick?
So they say that I think I mean, the claim is that it's the easiest to find out a modification for the final layer.
Yeah, that I understand. So
That is very clear. Yeah.
you can modify the final layer or the layer before that, and then see if it fixes this or not. Then the question is, what happens if it doesn't fix it?
Correct. So I think the
If it doesn't
constraints are
fix,
such that this thing will
what
be
would,
fixed.
you
We
know,
can
right?
If
explore
you
other.
find a solution, it will
then
definitely
you
be fixed.
explore
Yeah.
the layer. Then you will have to go one step
Yes.
earlier. So
Yes.
yeah,
Just a problem will be like if we go one step earlier, then we will have another layer which will have another ReLU,
correct.
and we will have an optimization. We have to do something which with the non-linear input. Here, what they're doing is after this is getting so simplified, we are just using LP solver
No,
tool.
that I understand. That I understand. But my question is,
Yeah.
what if it does not get fixed?
It will get fixed, right? That the way the constraints work is that the solution will fix it for. It may not be small.
The weights
The
combination.
weights, or you're saying that there is always a way to, or there always exists some weights for which it'll get fixed. Yeah. That is the key. So there is always a solution modification for these weights such that the output will get fixed. Is that right?
No,
then-
okay. So what you're saying is
Then
that
I
what
don't
if
know.
this
Then
turns out to be
you're modifying it to fix the problem, nah?
correct? So you're saying that what if this
Question
turns
is,
out to be
either
unsat?
there always exists some solution for the weights that'll fix the thing, or it does not. So are you saying that there is with the ReLU, with the linear thing, etc.? Why should there be a solution that always fixes your desired output? Why?
Correct. No. So I'm not saying that. I'm just saying that either you will find a fix or it will give you unsat. In which case they don't go back. Correct. In which case they don't go back to a previous layer.
Then you have to go one previous layer, nah?
I mean, they don't do that in their experiments.
They didn't do that in their experiments.
Which means they give up?
Yeah, they give up.
Okay. So you don't agree? Why?
Yeah, I mean, so input by input, you can always just, like, if you're checking for one input, right? Because if you want to run this procedure for one input only, say some X, then you can always change the last layer to configure it for that input, right? So do you agree with that?
No, he was asking if
You
this
can
is
always
not
change the.
problem.
Yeah.
So you're saying that for one, if you want to fix one input, there'll always be a solution?
Yes, I think so. Or at least it feels like there should be enough room to
That's what we are saying, right? That either there is a solution or it will tell you that it is unsat.
Yeah. So the point is that, so you're just trying to do this for a subset of inputs, and for the other inputs, you're using minimality to show that
Correct. So they're relying on minimality to argue that look, the bigger chunk of the behavior will continue to be the same.
Right. So if this happens to not work, so they're restricting it to they're bounding the change you want to make to the weights, so that the behavior is mostly the same.
Correct. So they're putting some restrictions on.
So if you arbitrarily allow the weights to do whatever they want, then maybe it's completely not possible even if you do that. But that
Correct. There could be cases, you can construct cases where it's simply not possible.
Minimal modification, I'm not convinced that there should always be a solution. Okay.
Yeah.
I mean, especially if you're allowed only to do within a certain bound, why should there be a solution? Why should there be a guaranteed way to fix it the way that you want
there
it?
is a use case where they haven't found a solution. I mean, they can try to get close enough, but if getting close enough is having a sacrifice cost of violating some other points, violating the same.
Okay. So let's move ahead. Yeah, because it's getting late.
Yeah. So Yeah, for L infinity norm, this comes to be a linear problem showing there. And for L1 norm, it still has some absolute value components which can be solved using some specified engines.
No, wait a minute. Why should for L infinity
just
norm, the verification problem
just
should
the
be
next slide.
linear? Because there is a max function for
Yeah,
L infinity.
max function of
Yes?
mod. So, and just the next slide, I'm showing the constraints for L infinity norm.
But the statement itself, I don't agree. Why should it become completely linear?
Because suppose have L infinity norm, that means the delta is equals to maximum of mod of Wi's, right? Right. So Wi will be from minus delta to delta. So this is one inequality. And in that way, I have some, if there are k many widths, I have some.
But the max function itself is not linear.
But from the max function, I can get some independent constraints. I just am showing it there.
Okay, go ahead. No, finish the previous slide and then you come. Yeah.
Like it's linear in Wi's, the variables Wi's. So
if you are taking L1 norm, suppose in that case, your equation will be a summation of mod of Wi's. Now, if you're trying to optimize it, you have to optimize in some other way. You don't have a linear, it is a not linear solving approach, right? It has absolute values in it as a component.
Yeah.
So, like, this is the easiest case. Like, you can completely solve using LP solvers. So I'm just about to show the constraints in the next slides. Huh? It's like, yeah, the minimal modification problem for L infinity norm can be formulated like this. Suppose this was my delta. As we said, like after modification, we have, what did we get? The weight matrix was changed. And that L norm of the neurons, I mean, everything else is same, just the Wi's are introduced. So the L norm would be what? Max of mod of Wi. For suppose four weights newly introduced. So for all this, you just take the max of this, suppose is M. You're trying to minimize M given this constraints. Where for the given input, that 3, 4 input, remember my second layer nodes were 0 and 2. So my third layer was like, it was supposed, the V31s was supposed to be this and V32 was supposed to be this. Suppose that this was 0 and 2 in the previous computation. So V31 is 1 plus W1 into 0 and this minus 1 plus W3 into 2 and V32 accordingly. So this is my V31, this is my V32 and my target is that V31 is greater than equals to V32. Ignore this one. So this is the problem setup which we have arrived at. So that is why we said like the max norm, the infinity norm is taking the problem to a linear setup. While suppose if we are using the L1 norm, in that case what would happen? We have to minimize M, where M is equals to summation of Wi's, summation of mod of Wi's, which may take some other strategies to solve it, not a LP solver. Right? So for this minimization problem, we have an optimal solution to be this. Optimal solution means we got the weight assignments and we will put this assignments to the modified network to get the modified network from the original one. So this is how we are modifying the network. And okay, watermarks. For watermark resilience, we are using this. What is a watermark? It is an input point to a DNN with a specific label L, which is a secret input. Like for that particular watermarks, for that their specific labels is only known to the person who is in the business. So that is actually his flag of ownership to that particular DNN which he has developed. So a watermark resilience is a set of watermark is, we say, is delta resilient if for every DNN n prime, if we are getting within this delta, whatever n prime we are getting, this is also L norm, it holds that nxi is equals to n prime xi. Means that modified neural network and that original neural network will label the watermark as the same. So this is the set of this watermarks, we are saying this delta resilient if this happens.
So are you saying that for this watermark resilience encoding, you always L infinity works? You always need L infinity?
No, sir.
No, then?
We can at max try till
No,
this.
no. I'm trying to understand the third bullet. Your title says watermark resilience. And your third bullet says
case,
that
yeah.
the minimal modification for the L infinity norm can be
Yeah.
encoded this. But that doesn't mean that, I mean, for watermark resilient also, you may need L1, L2, L3 is also possible.
Yeah, because we have done it using L1 also. We have
Okay.
done this using L infinity.
Okay, so only
also.
this thing. Okay, so you have to move fast now. So I don't know how many more slides you have. It's already
sure.
6:30. Yeah.
So given a specific DNN and a set of watermarks, solving this modification can serve two
I don't think you
purposes.
can go through all the 27 slides. Okay, so I see.
Sure.
So you will have to skip some of the slides and.
Yeah, minimal repair. Minimal repair is what we have explained before also. The formulation of minimal repair is, suppose I have a DNN which has a set of erroneous points and their set of correct levels I know. Now we seek to have a changed DNN which is very close to n. That is, we say n and n prime is the difference, L norm difference is minimal, such that in the changed DNN, all the erroneous points are getting correctly labeled. So this is a minimal repair. Yeah, so this is our implementation. We have taken the trained a watermark DNN over MNIST digits. And yeah, these are the assumptions. We have created a set of 100 watermarks. And for each of the watermarks, we have the assigned labels. This is the standard MNIST input, and these are the watermark inputs. So this is tagged as 5, 4, specifically by the owner.
What is it that you verify in watermark? If you remove watermark, if you remove the watermark.
If I remove the watermark means like.
Then you should get the original thing.
If I can easily remove the watermark, that means that particular neural network is not properly authenticated.
So you want to make sure that
yes.
that does not happen.
Yes.
Yeah.
Yeah. So yeah, removal is like for each watermark, we found the closest n prime such that that watermark is misclassified. I mean mislabeled. So that is where I have the things. As I said, like we can do it using L infinity norm and L1 norm. Here we can use some standard LP solver. Here we have to use some sophisticated engines. So,
yes.
So from
L infinity is easier.
Yes. So some of the observations are in the original network. Suppose the watermark is getting like the minimally modified network classified every single watermark to the label that was assigned the second highest score by the original network. That was one observation. And in L infinity case, some more resilient watermarks were approximately 26% more difficult to remove than others. For L1 case, it is even more. And this we are coming next. Yeah. Okay, no, this is 0.330, 0.32, 0.34 that way, and this is 20 to 24. Why?
No, what is it? What are the two axes?
Okay, this is the watermark image. I mean, suppose we have seen the effect. I mean, we have removed one watermark. We have checked for which delta we are first getting the n prime, which is misclassifying.
So the delta, so the
delta
y-axis
is the delta.
Is delta. So.
And we have just like towards the increasing order of their resilience. I mean, towards the increasing order of the delta value, we have plotted the points. One thing is, suppose this is the range is 22 to 34. Here the range is 0.30 to 0.38. Actually, why? Because in this case, the delta is being computed by, suppose, the new weights we are assigning, and we are adding up all of the weights, all of the absolute value of all of the weights. So it is getting blown up. Where in this case, we are taking only the max of the absolute value of the weights. So the change is more prominent here than this. Yeah, that is what is written here, though. Suppose. Yeah, this is the effect of removing watermark on overall accuracy. For L infinity, it's like kind of like minimal and maximal changes are 0.3 and 0.38, while that for L1, the change is, the variation is huge, 21 to 35. And this is average accuracy reported, 97, 87, and 94. For removing multiple watermarks, it's just we are taking arbitrary number of watermarks, and weights are changed to cause misclassification to it. And for that, what we have seen, it's kind of unstable after removal of 5 watermarks. So we have focused on what has happened after removing, we are removing 5. This is the change in accuracy when solving for L infinity, and this is for L1. Removing undesirable behavior is another. So it's like one collision avoidance system we have taken, where there was one property that specifies certain conditions, and we got an input x0 which is anomalous, like which is violating the property, has been discovered, and we have to modify that for this particular DNN. So yeah, this is what I was saying. This is how we are repairing. We have this this property, we have the given input, we have the network. So first we have assigned the input as set in the set S and N as N prime. We use a verification to check whether this is satisfied by this N prime. If this happens, if this phi holds for N prime, then we are returning this as the minimally modified using verification. Else, what we are doing is we are adding the newly discovered point, which is giving some faulty results for the N prime which has been constructed. And N prime is, then we are assigning to N prime the minimally modified N, so that this holds for all the points in the faulty. I mean, every time we are taking the faulty point set and we are modifying it by verification, then we are trying to test it with the points. If there is any validating point later, we are also adding it up to the S. Yeah, so this actually they ran after the first iteration. This is the one age. This saw change in one age. After the second iteration, this saw a change in second and one age. And here there was one slight change in two ages, and it didn't converge till the end for this approach. So yeah, related works are this augmenting a malfunctioning DNN with decision trees that determine when a patch should be applied, and correction of DNNs using an iterative encoding into a sequence of max SMT instances. And also for the watermarking, we have a lot of approaches to build these watermarks, backdooring digital fingerprinting framework or adversarial frontier stitching. We can use this technique to check the resilience of the watermarks being formed from these different approaches. This is the repository. The techniques can be extended for multi-layer changes to a DNN. That is one scope. And also, we were always bothered about the non-linearity and non-convexity. Is there any possibility to break the DNN into smaller DNNs and try to modify the decomposed parts and then accommodate the results together and get something? There is one future work.
That applies only if you're L infinity, it's always doable LP. Yeah.
Yeah, if L in infinity, we are getting the LP.
But otherwise,
we had one discussion about whether if we are not getting a minimally modified network at the last, so could we do this before?
Yeah, then
in
you
that case,
may
it
need
is
to
leading
split.
to So additional use cases beyond this two could also be identified. So we have marked this two, and we could also get something else from this. Yeah, that's it.
Okay, thank you very much.
Any questions? Anything?
I think there have been plenty questions. Okay, so and if there are, you can always contact her.
I know you have.
So this is the last class for the course. Thank you very much for all of you for attending these long presentations and asking questions and so on. So now...
Shayantan is not going to present?
What?
Shayantan is not going to present?
No, we don't have enough slots. Firstly, he got a job and he's flown the coop. Okay, so he's not here. I think he's in Pune, TCS Research. And Ankan, I mean, there was one thing that we had, but we skipped. I mean, Gohan's presentation that Madhukar was going to make, that was especially relevant for you, Avik. I mean, the thing. But
but I think we should discuss it sometime. I'm willing to make, this time.
No, but go ahead, Madhukar.
Yeah, I just saying that, because of the ongoing exams and the end of semester rush here, I couldn't do it. But I think this is an interesting discussion that, that paper can lead to. And I think we should do it anyhow.
What we have decided with you, Avik, is just a small subset. Madhukar, you and I, and Gohan, who's also interested in that, unfortunately could not present, have, Madhukar will present the paper for us. Okay, so we will have how to comparison of the things and what is it that can be done, something that some improvisation or something that can be done. Okay, so anyway, so with that goal, whether you want to get involved in that change or not, that's up to you. Okay, but at least for the presentation and for getting your, so you could add some of your thoughts there. And in that explainability area, that Gohan wants to do something. So, after we hear Pareto, what is it that we can do? Okay, so so that is something that we're going to very soon schedule, and that presentation, if you could be there and attend that presentation, then give your feedback, and then that will be, good. I don't know how That has to be done a little bit soon. Already Friday, but next week is exam week. We'll be busy, I think. No? It starts from 27th, which is, oh, there's still, but today is 24th, 25th, 26th is weekend, no? So if you can do during the weekend, then it is okay. Yeah, let's see. Let's discuss it separately. Okay. So thank you very much for, patiently attending and then encouraging other speakers, including yourself. And hopefully you can do the write-up, okay, so that'll address some of the points and deficiencies that you will not get to. Okay, that is where we will give you those questions, okay, based on that. So that make special effort to address those questions. I mean, the whole idea is that you should, for all the effort that you've put in, do make sure that you write it up so that you can get a better understanding of what you have actually presented. That's the idea for the thing. Yeah. No. I have not sent the list of questions. Okay. Once I get from the mentors, and I have, I will think about and send the questions. Yes. Yeah. Yeah. Because I just want to upload something there. Yeah. Okay. Thank you. Thanks, Madhukar.
Yeah. Thank you, sir.
Yeah, we will schedule that presentations. When is the earliest you could do? I mean, you guys can leave. Okay, just a week. Yeah. When do you think that you could do? Is Gohan there on the thing? I don't know if he's.
I'm here.
Yeah. So when shall we have the presentation, Madhukar?
Yeah, I think I'll need some time because I think this is the end semester. There's a lot of grading work.
Yeah,